Now this session we really only have one goal in mind. We're trying to show that the infinite set of positive rational numbers, in other words positive integers m over n, and m and n, they belong to the natural numbers, the positive integers starting 1, 2, 3, dot dot dot. Right? And we're trying to show that that infinite set is countable. And what does that mean again? Well, it means that you can form a correspondence with that set, big Q, the set of positive rationals, that you can form a correspondence between that set Q and big N, where N is the set of natural numbers, well, the natural numbers. Okay? So we're trying to prove that big Q is countable. So what we have to do now is to show that, how to create this pairing, how to create this correspondence, how to pair off each member of Q, in other words an element of the form m over n, where m and n are positive natural numbers. Okay, so how to pair off each member of Q with a member, one member of n. Right? It's a correspondence. It's a bijection. So we have to show that bijection. Actually do it. Right? So effectively, we have to show that Q is countable. In other words, and to do that, we have to show there is a bijection. There's a correspondence between Q, big Q, and big N. Right? That's what it boils down to. So how to do that? We're sort of proving that in a sense, illustrating how it can be done. Well, we will actually do it. Well, one strategy is just list all elements of Q, okay, and then just pair them off one by one with the elements of N. Okay, so you have, it's the essential idea. So you have your first element of the set Q, pair that off with the element 1 in big N. And then you take your second element of Q and pair that off with the element 2 in big N. Take the third element of Q and pair it off with the number, or the member, the element 3 of N, and so forth. Okay? Now, that's easily said. So, but how do you go about listing the elements of Q to be able to pair them off? You could imagine a column, or say two columns. So imagine a table with two columns, and in the first column you have the elements of Q, and in the second table you have the elements of N, and they're paired off. Each element of Q has its pair, an integer, positive integer, or a member of N. Okay? Now if you can do that, you've got a one-to-one onto mapping, you've got a correspondence, you've got a bijection, and therefore you have your pairing, and therefore your Q is countable, which is what we're trying to show. Alright, well, there's a trick. How to list. The problem's boiling down now to how to list Q, the elements of Q. How to do that so that you don't have any repeats, and particularly, and this is the major point, that no element of Q is left out. So how can you ensure that the list of the elements of Q that you make includes all elements of Q? You don't want to leave any out. So here's a way of doing it. You create Now, this is a technique, if you like, a device, to allow us to list all elements of Q, all positive rational numbers of the form m over n, where m and n belong to the natural numbers. So the positive rational numbers. You form an infinite matrix. So the number of rows, the number of columns, infinite. Okay, and you do it using the following style. So the elements in this infinite matrix, they are rational numbers. They're of the form m over n. Or let's say they are of the form I over j. Okay, that's the usual. Because we're going to use I and j as indicators in the matrix. So here's an example of the infinite matrix. We've just got the upper corner, and dot 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 and dot dot dot, that way, and dot 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 this way. So in the first row of this matrix, for the numerator, the one above the division line, in the numerator is the denominator underneath, but in the numerator, in the first row, we're just going to put all ones. Okay? And in the second row, the numerator will all be 2's. Okay? And in the third row, the numerator will all be 3's, and so on. So in general, in the the ith row, the numerator they'll all be I. They'll have I in the numerator. Okay? Now a similar statement for the columns. Now this is the first column here in this infinite matrix. Now this time, because it's column 1, the denominator, the number below the division line, so the denominator will now be 1. So 1, 1, 1, 1, 1, so on, dot, 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 all ones. Okay. Now in the second column, the denominator, they're all 2's, 2, 2, 2, 2, 2, dot, 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 dot. And in the third column, there will be 3's in the denominator, the number below the division line. So 3, 3, 3, 3, 3, and so on. Now, okay, now generalize that. Now go to the j'th column. Okay, so down here somewhere. So all its denominators will be j, right? Okay, now let's generalize those. Go to a general element, the ijth element in your matrix, the ith row and the j'th column, right? So it's sort of like coordinates. Your I and j then sort of become coordinates in your matrix. So I ask you now, what is the rational number, the positive rational number, that is situated at the ith row and the j'th column of this infinite matrix, given what I've just been saying before? Can you see that it will be, now it's in the ith row, so therefore the numerator has to be I, okay? And it's in the j'th column, therefore the denominator has to be j. You put those two together, and therefore that rational number at position the ith row and j'th column, that element of the matrix has to be I over j, right? So now by having an infinite matrix with an infinite number of rows and an infinite number of columns, so your I can be all possible values, your j can be all possible values, so that infinite matrix will contain all possible, systematically all possible positive rational numbers, right? So by using this technique, this infinite matrix technique, we know. So the list of all rational numbers is just the list of all these elements in the matrix. Has to be. Right? Okay. Now, all right. So now, how to form the list from this infinite matrix? Well, one suggestion, a bad one, is list first the first row, followed by the second row and third row. The downside with that, of course,